So I've got a linear transformation here, which is known as T, and you notice here I've got complex two-dimensional plane to another complex two-dimensional plane, but our transformation T with regards to x and y is known as 2x minus 2y and 3x plus 4y, and these are all real components. So the clue here says that our eigenvalues are going to reap complex numbers. So let's see what happens. So first of all, let's find the eigenvalues. So we need the characteristic equation. Now the characteristic equation, if I call that just characteristic equation, what we normally do is we get the determinant of a minus lambda I and set it to 0, and then find solutions for lambda. Now there is another way which we can do this, and what we can do is we go straight in. Rather than take the determinant of this, we start off with a lambda squared as its 2 dimensions, and then we subtract the trace of a times lambda, and then we add the determinant of a and set that to 0. Now these will yield the same characteristic equation and give us the same solutions. So if you check the link below, I'll show a video of how this yields the same as this in all cases. So first of all, let's go into this. Now the trace of A is just the sum of the diagonals of the matrix A, and determinant is just the determinant of A. So first of all, let's set out what A is. So A, let's write it down here. So A, what we do is we set this up from left to right, the coefficients of our linear transformation. So we've got 2 and minus 2 in the top, and 3 and plus 4 in the bottom. So 2 and minus 2, 3 and 4. Okay, now the trace of A is just the sum of the diagonals. So therefore, trace of A just equals 6. Now the determinant of A on a 2 by 2 matrix is just these two multiplied together, subtracted from these two multiplied together. So 2 4s are 8, and then subtract minus 6, which gives us 14. So that's our building blocks for this equation here. So let's write this up now. So characteristic equation, that will now give us lambda squared minus 6 lambda, and then plus the determinant, which is 14, and that equals 0. So now we need to solve for lambda. Okay, this is not factorable. I can see straight away with 14 and 1 and 7 and 2 that's not going to work. So let's go straight into quadratic formula. So we'll have our A is this one here, B is the minus 6, and C is the plus 14. So minus B gives us 6. So our solutions are lambda equals minus minus 6 plus or minus square root of B squared. So minus 6 squared is 36, minus 4AC. 4 times 1 is 4, times 14 is 56. And then divide that by 2 times A, which is just 2. So we see straight away here 36 minus 56 is minus 20. So that's going to yield complex solutions which are normally conjugate of each other. So that's where the complex two-dimensional comes in. Okay, let's go for this one. So lambda equals 6 plus or minus 36 minus 56 gives us minus 20. So square root of minus 20 is, take an I out of it. So let's just take I out of it, and then square root of 20 over 2, which then gives us 6 plus or minus square root of 20 is same as square root of 5 times square root of 4. Square root of 4 is 2, so it's 2 root 5. So plus or minus 2i root 5 over 2. Now we see we've got 6 divided by 2 gives us 3, 2 divided by 2 gives us 1. So therefore we've got, take them out, we get a 3 there. Eigenvalues, lambda 1 will equal 3 plus I root 5, and lambda 2 will equal 3 minus I root 5. So that's our eigenvalues. Now we need to work out the eigenvectors. Now the eigenvectors, we know for that one, we go a minus lambda I multiplied by standard vector x and y, as we've got x and y, and then set that to 0. Okay, so a minus lambda I. I is the identity matrix, which is 1, 0, 0, 1. Multiply that by lambda, we get lambda 0, 0, lambda, and then subtract that from a, we'll get, this one will now become 2 minus lambda minus 2 and 3 and 4 minus lambda. And then the vector v will be just x and y, and then that's set to 0. Okay, right, now for each of the eigenvalues we've got very similar, they're just conjugate of each other. So I'm going to work on lambda 1 first of all. So now in here I will have 2 minus this eigenvalue here. So I've got 3 plus I root 5 and then minus 2. So this takes up quite a lot of space. Then I've got 3, so let's put that there, and then 4 minus this thing in brackets. So 4 minus 3 plus I root 5, then multiply that by x and y, and that is 0. Okay, let's simplify that off. First of all, let's make some space on the board so we can got a bit of space to work with. So let's simplify. So real components are 2 and 3. Subtract 2 from 3, get minus 1. There's only one imaginary component, so we've got minus I root 5. 3 on this one will stay. Minus 2 there is good. And here, real components are 4 and a 3, so 4 minus 3 is 1. And then minus I root 5. Okay, multiply that by x and y, and that's still set to 0. Okay, let's have a look what we can do here. So we've got minus 1, minus 2 and 3 here. Now what I want to solve for x and y, I want to do Gauss-Jordan elimination. So ideally I want a 0 here, maybe a 0 here, turn this into 1. So for good things to happen, now this is the coolest part of this video, what I want to do is find the common multiple of the real numbers, which in this case are 1, 2 and 3, it's going to be 6, and I want the reciprocal. So something over 6 is what I need. Now because this is a minus 1, I want that to disappear. I want to plug in a minus 1 here as well, so minus 1/6. And now here, as I've got I root 5, I want this to disappear into a real number. So I want the conjugate of that, which is plus I root 5 and also over 6. And what I'm going to do now is do Gauss-Jordan elimination. And my first input will be to get to multiply that by that. Now you'll see good things will happen when we do this. So let's just bring this matrice down. So minus 1 minus I root 5 and minus 2, 3, 1 minus I root 5. So let's just concentrate on this and get that into some kind of row echelon form. Now this is our all important number here in the box. That's what I want to deal with. So if I call this row 1 and this row 2, row 1 I'm going to multiply by this number. So row 1 becomes row 1 multiplied by this number here. So I'm not going to rewrite it, I'll just put an arrow so you can see what it is. So let's go with that. So first of all, let's deal with this complex and real part here. So I've got minus 1 minus I root 5 multiplied by this, which is minus 1/6 plus I root 5 over 6. Okay, let's go with this. So minus 1 times minus 1/6, that gives me 1/6. Minus 1 times this I root 5 over 6, that gives me minus I root 5 over 6. Now look what happens here. I've got minus I root 5 times minus 1/6. So that's going to give me positive I root 5 over 6. And then these two are going to cancel each other out. So that's the first cool thing that's going to happen. And I need to multiply these two complex parts. So minus and a plus. So I've got a minus there for the moment. Root 5 times root 5 is 5. Divided by 6 is 5 over 6. Now just check the sign because we've also got these i's in here. So I times I squared is minus 1. So therefore we need to change this sign to a plus. So these cancel. And 1/6 plus 5/6 just gives me 1. So now I can just put 1 in there. So I've got 1, then minus 2 times this. So minus 2 times minus 1 over 6 gives me positive 2 over 6, which is a third. And then minus 2 times I root 5 over 6 gives me minus 2/6 root 5, which is minus 1/3. So minus 1/3 I root 5. So I'm just going to write that as minus 1/3 I root 5. Don't need the 1 in there. So this will now stay as it is. 3 and 1 minus I root 5. Okay, now I need to do something with this to get it into 0. Well, we can see straight away if I multiply this by 3 and subtract it from that, I'll get a 0 there at least. So now I want row 2 becomes row 2 minus 3 times row 1. So let's go with that. So top row is going to stay 1, and I've got 1/3 minus I root 5 over 3. So 3 times 1 is 3, subtract it from that gives me 0. Perfect, I've got a 0 in this corner. Now multiply this by 3, I've got 1 minus I root 5. Now if I subtract that from this, I've got 1 minus 1 gives me 0. And then minus I root 5 over 3, sorry, minus I root 5 minus I root 5, that will also then cancel out and give me another 0. 0 plus 0i. So that's the result. I've got two zeros on the bottom, which is perfect, and just an x and a y component here. So now back to here, bring this back down, x and y, 0, 0. Okay, so now let's just multiply these up. So I multiply that with x, I just get x, and then my y is 1/3. So I need to add 1/3 minus I root 5 over 3 y equals 0. Okay, let's get rid of this fractional part. So now I've got 3x plus, open brackets, 1 minus I root 5y. Remember, this is just the coefficient for y, and then that equals 3 zeros, still 0. Okay, right, let's clear the board at the top and let's try and solve for this. Okay, right, let's bring this onto the other side. So 3x equals, right, if I bring this on the other side, I can change the signs of all of these. So I'll get minus 1 plus I root 5, and that's for y. Okay, well, to solve this now, if I take this coefficient and plug it in for y, so if y equals 3, if y equals 3, then x will become this one. So then x equals minus 1 plus I root 5. So then my eigenvectors, I can put my result here for lambda 1, that equals, so x is this one, so it's minus 1 plus I root 5, and y is 3. Now, for the eigenvalue of 3 minus I root 5, my result is just going to yield me the conjugate of this one. So I can leave you guys to work that out if you like, just to check, but that's what we will get for the second eigenvector for the minus I root 5. Okay, and that's where we leave it.